In order to really understand how your heart functions, it's important to understand the electrical activities that take place in the heart and its chambers. And so we can actually detect the electrical current in the heart by means of placing electrodes on the skin and measure the electrical current using an electrocardiograph. And this electrocardiograph is going to result in a recording referred to as electrocardiogram. And so this video today is going to help you interpret the different components and deflections in this electrocardiogram trace. So when you look at a typical trace, you're going to notice three principal deflections. What we call the P wave, followed by a big event that is known as the QRS complex, starting with a small downward deflection, Q, followed by a tall, sharp peak, R, and then followed by a final downward deflection, that is the S. And then the third principal deflection is what we call the T wave. And so this is going to be repeated over and over as long as you're recording from the heart. And a typical interval between two R waves is around 0.8 seconds. So the purpose of this video is to really understand what is causing the P wave, what is causing the QRS complex, and finally what is causing the T wave. And so we're going to be looking at these principles and analyzing not only the electrical activity that takes place to result in these deflections, but we are also going to trace blood flow through the heart, understand which heart valves are open versus closed, and then finally superimposing this with the cardiac cycle phase. So let's begin. Let's start with the P wave. So in terms of the P wave, and if you remember from the electrical conduction system of the heart, we've looked at a specific pathway from which electrical activity originates, where we call the pacemaker cells, and then how the current travels. So this is pretty much going to follow this electrical conduction system step by step. So let's begin. So the P wave, if you remember, electrical activity starts at the pacemaker cells present in the SA node, the sinoatrial node. And so this sinoatrial node is where the signal is going to originate. So it generates the signal. And this signal is going to spread through the atria and depolarize them. So spreads through atria. Again, left and right atrium. So we call them plural, the atria. And this will result in atrial depolarization. So the P wave is generated by atrial depolarization due to the electrical activity of your SA node. Now, what is this going to result in? After the atria depolarize, this results in what we call atrial systole. And for each chamber, you're going to notice that they are going to contract and then relax. Contraction is known as systole, and relaxation is known as diastole. And so systole is always going to precede diastole. So as a result of atrial depolarization, this is going to result in atrial contraction or atrial systole. Now let's understand where blood is flowing during this phase. Well, if atria are contracting, we know that they're going to need to push the blood into the ventricles. And so this is pretty much what happens at the end of the P wave. So blood flow is going to move from the atria to the ventricles. I do want to mention though that the atrial depolarization, when the atria contract, they are actually pushing the final third of blood into the ventricles. And this is because blood is always filling the ventricles from the atria during this time. And it's the atrial contraction or the atrial systole that pushes the last 1/3 of blood volume into the ventricles. And so next up, let's look at the heart valves. So if you remember a little bit from the heart anatomy video, when the blood is moving from atria into ventricles, the valves that are between the atria and the ventricles will need to be open in order to allow blood to pass. And this means that your atrioventricular valves, bicuspid or mitral, and the tricuspid valves are open. Okay. Finally, the cardiac cycle phase, this is what we call ventricular filling, because during this time your ventricles are being filled with blood, both right and left ventricles, and it is the atrial depolarization followed by atrial systole that results in the completion of this filling. And so the volume of blood found in the ventricles at the end of this phase is what we call the end diastolic volume, EDV. And this is defined as the volume of blood found in the ventricles at the end of ventricular filling. Now, let's move on to our second deflection, and this is another large event that we call the QRS complex. So we know from the previous deflection, the P wave, that the atria have already depolarized, followed by contraction, and then they filled the ventricles with blood. So now our second important event is that now it's the ventricles' turn. So the ventricles are going to be contracting in the next event, but contraction has to be preceded by depolarization. And so in terms of electrical activity, now this is where your AV node, the second component of your electrical conduction system, is going to send electrical impulses to the ventricular myocardium, the muscle of the ventricles. And so what is this going to result in? Call this ventricular depolarization. And so the big event that is going to follow this QRS complex or ventricular depolarization is what we call ventricular systole. Meaning ventricles are now going to contract, and this typically occurs during the ST segment. So as a result of ventricular depolarization, the QRS. I do want to point out that after your atria contract, they need to relax. And so this here is also going to overlap with atrial diastole, also taking place in the QRS phase. However, because this atrial diastole is such a weak signal, it's usually overshadowed by the large ventricular event, but it does take place at the same time as ventricular depolarization. So now let's move on to blood flow. So where is blood flowing during this time? Well, we know that after blood enters the ventricles and the ventricles depolarize, now the pressure inside your ventricles is higher compared to the atria. So blood is now pooled into the ventricles, and now they are ready to start pumping, contracting in order to send the blood out of the ventricles into the two vessels, the aorta and the pulmonary artery. And so here we actually have two phases of the cardiac cycle, but let's talk about blood flow first. And so what you expect is that blood is now found in the ventricles. And so we're going to break this down into two phases, because when blood is in the ventricles, as I mentioned, the pressure of ventricles is going to increase. So it's going to be higher than the pressure of your atria. And so this is going to result in the shutting of your atrioventricular valves, so the bicuspid and tricuspid valves. And so as a result, AV valves are going to close due to this change in pressure, and the ventricles are now filled with blood. And so when the AV valves close, this is going to result in the first S1 lub sound of the heart. And so this takes place during the QRS complex. This is also called, in terms of the cardiac cycle phase, this is what we call isovolumetric contraction. And then we also have a second phase, which is right at the end of the QRS complex. And this is when your ventricles are going to start to eject the blood. And so here I do want to point out that we have yet again another phase in which ventricles are going to start to eject blood out of the ventricles into the aorta and into the pulmonary artery. So back at blood flow, we're going to say that ventricles are going to push blood to the aorta and the pulmonary artery. And I want to mention that this yellow that we're going to be writing is going to be at the end of the QRS complex. Now, in terms of the heart valves, since blood is leaving the ventricles, you're also going to have the opening of your semilunar valves. And these are going to be your aortic semilunar and the pulmonary semilunar. And so during this time, the cardiac cycle phase is called ventricular ejection. Right? Because your ventricles are ejecting the blood to the corresponding blood vessels. Okay, and this will occur because the pressure of your aorta and the pulmonary artery are now greater than the pulmonary ventricles, than the ventricular pressure. Okay. So pressure in aorta and pulmonary artery is greater than the pressure of the ventricles.